Hi there, and welcome to our talk about how we went about enabling data scientists during the COVID crisis, featuring our data analytics as a service platform using CNCF technologies. My name is William Hearn, and I am the CS4 on the Cloud Native team at Statistics Canada, working as a cloud architect with a focus on using open source cloud native technologies to try to improve how governments deliver services to Canadians.
I should note that this presentation will focus more on the architecture of the DAaaS platform itself, though we will be showing a few high-level demos. To see further examples of our platform in use from a data science standpoint, please attend Session 7B, Advanced Analytics Workspace, Rapidly Deploying Data Science Capabilities in the Cloud. Of course, none of this can happen unless you have great teams working together. A collaborative effort of disparate teams was started at Statistics Canada, which consists of the Cloud Services Enablement Project Cloud Native team, the Data Analytics as a Service project, the Data Science Division, and the Digital Innovation field. These close collaborations between the technical teams and our end users enabled us to quickly advance the platform and to build the components that they needed in a timely fashion. We would also like to quickly thank the broader Kubernetes, Kubeflow, CNCF, and Golang community for all of their help in getting us this far. The challenge we were faced with was how to enable data scientists, both internally at Statistics Canada and other external partners across government, to perform data and analysis of various data science-related workloads, in particular addressing the immediate needs of StatsCan's COVID-19 response. The platform also had to be set up quickly as well as securely in a public cloud environment. Therefore, one of our main goals was to utilize the components already created and leveraged at Statistics Canada. These include the Statistics Canada Kubernetes platform, which would be a whole talk in and of itself, but is in essence a managed Kubernetes installation along with various platform tooling installed. For your benefit, we have added links to our platform documentation, as well as a link to our Stratosphere 2019 presentation, which was solely on the Kubernetes platform itself. Then we have DAaaS analytics specific tooling such as Kubeflow, Jupyter Notebooks, R, Selden, and Shiny, to only name but a few, and will be discussed in more detailed length as the presentation goes on. As an overview, it should be noted that all tools and processes discussed during this presentation have been completely open sourced on the official Statistics Canada GitHub organization. Development occurs in an agile fashion on GitHub, where we have 1 to 2 week sprints, daily stand-ups, and weekly retrospectives. All issues and feature requests are tracked in GitHub issues, pull requests are matched to GitHub issues, and these are attached to the GitHub project, along with a Kanban board. Additionally, we presented this platform to the chief statistician and the assistant chief statisticians, who alongside with the data scientists who use it daily, were impressed and expressed their interest in seeing this platform grow across government. The data analytics platform is built on top of a set of fundamental services. Let's talk for a moment about these services before deep diving into the analytical tooling. Here is a quick overview of the different tools in the platform. First, at the base, there's Kubernetes, the central orchestration layer and the connector between the platform and the cloud infrastructure. Next, we have the suite of security tools, which will handle policy enforcement, network security, and secret storage and generation. There is additionally monitoring and logging tools, which will provide observability into the health of the platform, as well as real-time metrics. Additionally, we have a series of packaging and deployments for both the infrastructure and application layers, where everything is executed through GitHub Actions. Beyond that, there are various data science tools, as well as the PaaS services that we integrate with. We use the Managed Azure Kubernetes Service, AKS, to reduce our cluster management overhead. For those without knowledge of Kubernetes, it is a desired state orchestration system, which integrates well with our automation processes. Kubernetes has support for user isolation via namespaces, which is important for a multi-tenant architecture. Although, please note that namespace isolation is not all that's needed for multi-tenancy, and other tools are required, for instance, network policies. Really, Kubernetes is a platform to build platforms. It provides extensibility via the use of custom controllers and custom resource definitions, CRDs. For example, we've created a profiles controller extension, which configures user profiles with credentials, configuration options, etc. We've also added a GPU toleration injector, which automatically configures tolerations for GPU workloads. And we also contributed Boathouse Flex Volume, which automatically configures notebooks with object storage configuration. Kubernetes also has support for a wide range of programming languages. Essentially, if it compiles, we can reconcile it. We've used, for DAaaS in particular, the following languages: Python, Go, Node.js, TypeScript.js, .NET Core, Java, Julia, and R. Our infrastructure is managed via automation using infrastructure as code and configuration as code methodologies. We utilize a mixture of Terraform, Kustomize, and Helm for the platform. The automation is entirely executed via CI/CD with GitHub Actions and controlled through a pull request review process. The review process itself performs checks like code linting, container scanning, which helps to identify CVEs in any container images being built through Trivy, the building of container images and pushing them to the Azure Container Registry, as well as the deployment of the application into the Kubernetes environment itself. It even expands into the analytics platform, where we have custom Jupyter Notebook containers running under Kubeflow, a self-service but gated deployment of our Shiny dashboards, and finally, as well as a web portal and other data science-related workloads that are deployed where needed. An interesting fact that we'd like to point out is that we've often tested rebuilding the entire environment from scratch. The last time we have done this, we rebuilt it in less than a day using Terraform, and even migrated over all the legacy user data using VMware's Velero. The platform contains a lot of security components and configuration. The major ones are Azure Active Directory integration, which helps us with our Kubernetes RBAC, Vault, Kubeflow, Portal, and other web-based services through OpenID Connect. There is Gatekeeper from the Open Policy Agent, which provides an enforcement of a range of policies throughout the cluster, such as authorized container sources, container permissions, volume mounts, no public load balancers, and so much more. All inbound traffic is TLS protected using Let's Encrypt certs automatically issued by Cert Manager. Additionally, we provide mutual TLS authentication for most inter-service communication, which is facilitated automatically via Istio, our service mesh. Continuing from the previous slide, additional security components are full audit logging provided by the Kubernetes control plane. All cluster and application logs are segregated into a centralized Elasticsearch instance. Daily automated cluster security assessments, leveraging CIS benchmarks and best practices through Starboard. And finally, dynamic credential generation and auditing provided by HashiCorp's Vault. Due to the larger amount of compute necessary for analytical workloads, we wanted to ensure we are maximizing our costs. To do so, we use reserve instances to reduce the cost of our base compute needs, which roughly saved us about 33% per year. We also support auto-scaling of compute infrastructure, whether scaling up and down based on active needs. And we limit workloads assigned to GPU nodes to those who require GPUs. To get a breakdown of resource utilizations per user per project, we also deployed the KubeCost system, which provides detailed billing information of Kubernetes resources that can be queried through an API and provides spending alerts. The following is an image of what KubeCost looks like, and we will be doing a deeper dive of this tool during the demo. What you see now in the following image is a simplified reference diagram for Azure that can be viewed later in more detail in the posted slide deck. This is a logical diagram of Statistics Canada's DevSecOps platform architecture, which is used for much more than just DAaaS, and in fact powers a lot of our cloud's SDLC. This diagram can be viewed in more detail later in the posted slide deck. The following are just some images that demonstrate the Kanban board, the CI/CD review process, and GitHub Actions showing the change in Kubernetes state. These images can be viewed later in more detail in the posted slide deck. Remember, Kubernetes is really a platform to build platforms. Now let's look at the analytics tools that have been installed into the Kubernetes environment to provide data science capabilities. Kubeflow is the main entry point into the data science tools. It provides a dashboard exposing access and control of Jupyter Notebooks, pipelines, experiments, model training resources, and so much more. Additionally, it provides self-service enrollment.
When you first log in, you're prompted to create a profile, and then you have full access to all the tools. You can even invite other collaborators into your space as well. Here we can also mention Kubeflow is not locked to a specific cloud or framework, as it can run on-prem, in the cloud, or both. You can also leverage existing platform as a service offerings to implement additional functionality. Kubeflow is essentially a universal control plane leveraged through APIs that facilitates machine learning. Jupyter Notebooks are the currently most used component of the DAaaS platform. In fact, we provide a variety of images to our users. These include minimal, geomatics, machine learning, and RStudio in both CPU and GPU variants. In addition, we also provide a desktop-like experience using images for geomatics and R. These images enable users to design, experiment, and execute machine learning processes. All the notebook images are maintained in a public GitHub repository, allowing administrators and users to perform updates to the images in a standardized process. All images are then built in an automated CI/CD system, which is then scanned through Trivy. Users are additionally granted some permissions in their notebooks. In particular, they have the ability to add their own packages and software, enabling self-service. Finally, our notebook system currently supports various storage mechanisms, which includes raw disk, PVC, S3 compatible mounts, Azure Files, Azure Data Lake, and Azure Blob Storage. Kubeflow, and really Kubernetes, provide an analytics orchestration system. All analytics components are pluggable, allowing for integration with any open source or platform as a service offering. In fact, we'll touch more on these components in the demo later in the presentation. Please note, this diagram of the MLOps pipeline is placed here for posterity, but we will be going through it in detail shortly. Let's talk briefly about what we learned over the past few months working on this project. But first, it should be noted that this project was geared towards quickly enabling data science during COVID, and its lessons learned will be brought back to the official Data Analytics as a Service project internally at Statistics Canada. This project had a large focus on user experience. In particular, we worked with our digital innovation team to build a web portal that is the main starting point for the platform. We then developed a series of documentation to assist users, especially since some of the technology is new to StatScan. We finally also provide support via our Slack channel and additionally through GitHub issues. Ultimately, our main goal was to make sure that the users of the platform are self-sufficient without requiring our intervention to get them started. There were a lot of positive lessons that we've learned throughout the project. Let's go through some of the major ones. The first is that automated scaling worked exactly as intended. When we needed extra compute, due to user demands, for example, the platform automatically adds another VM to the cluster. When that compute is no longer needed, it is automatically scaled down. Additionally, with respect to GPU nodes, due to cost, they are only added when needed and removed when unneeded, through the concept of node pools. The second is, working closely with our users allowed us to build exactly what they were looking for. Our users appreciated the direct line to the technical teams, and the technical teams benefited from direct access to our users. This culminated in the end product being described as the dream platform by the director of the data science division. Number 3 is, working with the open source community allowed for quick advancement of the platform. We were able to reuse the existing work of the community since we're not the first to build a data science platform on Kubernetes. We also contributed our improvements back to the community, enabling us all to move forward. Continuing on, we have number 4, where automation via CI/CD enabled rapid iteration and reuse of infrastructure components. And as mentioned earlier, it allowed us to quickly rebuild the entire platform in half a day. For number 5, we have support from key members of the community, for instance, by the Kubeflow co-founder and chief of open source at Microsoft, David Aronczyk, who reviewed our work and agreed with the strategic direction of the platform. We also have support from many large organizations, such as Google, Microsoft, IBM, AWS, who are all working with the Kubeflow community, as well as offering a managed Kubernetes service. Finally, for number 7, we have a self-service architecture, which enabled our users to accomplish their tasks without friction. They don't feel like their hands are tied. They don't have to wait for a while for an administrator to add a single library, etc. As an example, our data scientists are using our dashboards to provide data visualizations. Publishing them on our platform is as simple as a PR to a GitHub repository. There were a few issues along the way that took some time to resolve, and in that vein, there are still a few outstanding items that we can improve. The first would be Kubeflow multi-user support, which is still relatively new and doesn't extend to the whole suite of tools. So pipelines, for example, are not properly user isolated, though it is scheduled for the upcoming Kubeflow release. We are also one of the largest users of a multi-user Kubeflow instance, so we've hit some growing pains there as well. Finally, there are other areas where we're investigating to further hide some of the technical details of the platform, providing an overall better user experience for those unfamiliar with Kubernetes. The first would be mounting object storage as a local file system, which was recently completed, and others such as identifying other tools which can improve the user experience. For instance, a tool like Lens, which provides a rich UX and broad overview of the Kubernetes resources without needing to know the specific command line operations to view that information. At this point, it is now time to go over a few demos that will hopefully illustrate and provide you with more context on how the tools work. The following slide will illustrate the order of the demos we will be presenting. It will start off with Terraform, then go into Kubeflow, the setup of the profile, the launching of the Jupyter Notebook, and then finally into our Kubeflow MLOps advanced pipeline, closing everything out then later with our cost tracking tool. Let's walk through an example of our infrastructure change process, which involves GitHub and GitHub Actions. In this example, a team member submitted a request to increase the number of GPU nodes to 20. The request was made in a separate branch and submitted for peer review. Our CI/CD system added a comment with the delta, and then once reviewed and approved, it is merged and automatically applied. This pull request workflow has been working really well for all of our teams that have been working in the open. Now let's go through the first-time user experience. We'll first begin by logging in with our corporate Azure Active Directory account, which incidentally uses OpenID Connect. Entering the kubeflow.covid.cloud.backend.ca domain name takes us to the Azure login screen, where we will get an MFA challenge response. With our authentication done, now we should be greeted with the initial Kubeflow login screen. You should take note that we are asked one question, and that is what to name our profile. This will be used to create the associated namespace in Kubernetes. And then once this is done, we are placed into the dashboard where we can begin to use the Kubeflow system. Let's start with the most commonly used part of the system, Jupyter Notebooks. We first begin by clicking New Server, and now we agreed with the following screen. We're going to enter a name of Demo Stratosphere, and now we're going to select the appropriate image. In our case, we're just going to select the minimal CPU variant. We're going to leave the CPU and memory requirements alone for now, and instead of selecting an existing disk, we're going to create a new one of 10 gig size. We could also specify that this is a GPU node we wish to launch, but not for these purposes, and then we just click Launch. It will normally take up to a minute to provision this environment, of which we've just sped us up along to help us with the demo, and then in about 50 seconds it has came up. So what we're going to do now is just click Connect, and this will actually bring up the Jupyter Notebook for you. What you will then notice is we are greeted with the following screen. You can immediately start working with a Python, Julia, or R notebook. To further facilitate you, we have also added a range of tutorials and pre-created Jupyter notebooks that you can work from. For instance, right here, we're going to just click on the Quick Start notebook, and here are just some quick example commands to get you started. I should finally mention that we also have added a Minio folder, which is directly linked to our object storage. Later on, we will also be adding support for Azure Data Lakes and blob storage.
Let's take a deeper dive into other options available to us in our notebooks. If you launch a desktop image notebook, you're granted with a landing page. Connecting to the remote desktop instance opens a VNC connection right in your browser, giving you the familiar desktop environment.
You can also launch a Visual Studio Code environment as well, straight from the landing page.
Look at cube costs. Let's open up our environment. And at first we can see an overall glance of the cost of our cluster, broken down by month, broken down by deployment, by product, by namespace. What is our resource efficiency? Breaking it down further, we get memory, CPU, and disk cost per namespace. But we also get a bunch of suggestions for saving. So how can we save additional costing? And what is our overall health? And finally, we can generate a series of reports. And we can set up a series of notifications. So whenever a user or a namespace exceeds a certain threshold of cost, a notification is generated.
The Kubeflow MLOps repository contains examples of completely integrated Kubeflow end-to-end pipelines using GitHub Actions. Our focus was on the creation of pluggable components that can make it easier to build your own heavily customized pipelines, enabling more advanced machine learning projects. Looking at this diagram, the first component we are going to look at is a CI pipeline running through GitHub Actions. Going back to our repo on GitHub, we are going to click on the current build that is running since we did a commit recently. You should notice that the code quality checks have already run and linted our Python code before it gets built into a container in the build images step. The build images step itself uses Azure Container Registry to do the actual build of the container images. Some of the images we are currently building are for Databricks, TensorFlow in relation to pre-processing and training, and then some registration containers against Kubeflow, MLflow, and Azure Machine Learning for when we want to push our artifacts up to them. What we are going to do now is build our reproducible Kubeflow pipeline, which is created through a domain-specific language template. I unfortunately don't have time to go through this in detail, but it basically just describes all of the inputs and outputs for the various containers, as well as their dependencies. The build Kubeflow pipeline will compile the DSL and publish it to Kubeflow, as well as actually execute the run itself. Notably, our helpful little MLOps bot was even nice enough to add the model training section in our CI so that we can click the link and go straight to the run. Looking at our diagram, I have pointed out that we are now switching context to the Kubeflow pipeline. In our first step, we are going to use our Databricks container to launch the Databricks PaaS on Azure, pass it some parameters, and retrieve the output. The Databricks Spark cluster will then shut down again after the 20 minutes idle time. We could have just as well have launched Spark on our Kubernetes cluster, but Databricks does Spark really well, so it was nice to illustrate how we can interact with most cloud vendors' PaaS services. It does take a moment for the Databricks cluster to start, so I have sped up some of the output and then went to the Databricks service in Azure to show you that the execution was successful. The next two steps leverage TensorFlow, which will do both the pre-processing and training of about 1,000 images of tacos and burritos in order to get a useful model. The data will be served from a remote endpoint, so it can be constantly updated. It should also be mentioned that the TensorFlow metadata around the pre-processing and training is instantly being sent to MLflow. If you quickly take a look at the output of both the steps, you should notice that we are loading a data set as well as creating and training the model. Now, with the model pre-processing and training done, we are going to show further integrations by storing our model plus the whole lineage in Kubeflow and just the model itself in Azure Machine Learning and MLflow. Once the pipeline has fully succeeded, you can see that we call an exit handler. This will actually send a payload to our MLOps bot, which in turn talks to GitHub Actions. You can also take note of the run output, as well as the config section in Kubeflow, which shows you what inputs were passed to the pipeline. Going back to our diagram once again, I have pointed out that we are now switching context to the CD part of the pipeline, which again is triggered through the MLOps bot upon a successful Kubeflow run. The CD job essentially grabs the latest generated model that the CI process stored in MLflow and builds a scoring container image with that model. The model is then served through SoundLine Core through a custom predictions endpoint. In this example, further promotions to a UAT prod with Kubeflow serving have been intentionally left out.
Now let's test with the following image and see if our model is working correctly and will properly classify the image. I am simply calling the self-in-serving endpoint, passing a JWT token for authentication, and an image I'd like to get classified. You can see once the curl call completes that the image was correctly classified as a taco. Before I get to the closing of the presentation, the last thing I would like to show are the models being correctly saved in both Azure Machine Learning and MLflow. Unfortunately, I won't have time to show much more than that, but this should give you lots of ideas about potential integration. Finally, if we take one last look at Kubeflow, I just wanted to highlight you can export the whole reproducible pipeline as a simple YAML file and even get a nice lineage explorer detailing just how your data was transformed in the pipeline. Looking forward, we are excited to see the continued development of the data analytics as a service platform. We are keen to expand this platform beyond Statistics Canada and make it available to other government departments, as well as provincial, territorial, academia, and industry. The value in the platform is in its integration, and we're looking at expanding the current development to connect with equivalent and newer services offered by all major cloud vendors. Being part of the open source community is not just using open source tools, but also contributing back. As part of this project, we've already contributed many fixes, submitted issues, and even created our own open source tooling that we've shared with the broader community. Tools like Boathouse and Goopus Injector, which are an object storage wrapper that allows for you to mount volumes into Jupyter notebooks on the fly, and can even work with such tools such as Azure Data Lakes, Azure Blob Storage, and later other cloud service providers as implementation. Then we have the Jupyter APIs, which is a rewrite of the Kubeflow Jupyter APIs into a Go backend, which resolves some deadlock issues we were having in the current Python implementation. The following are some useful links that should help you get started with our implementation of Kubeflow and will be accessible in the posted slide deck on the Stratosphere website. Some of the links are, we have our Statistics Canada GitHub organization. We have a link to our brief technical summary, which discusses in a bit more detail how the platform works. We have some links to our user manual for the Advanced Analytics workspace, as well as links to community-oriented content and platform content on YouTube. Finally, we have some more technical links related to how we actually install Kubeflow in our Kubernetes cluster, which is the Kubeflow manifest. We also provide links to how our containers are generated for the Jupyter notebooks run inside of Kubeflow, which is the Kubeflow containers repository. And finally, we provide links given for our Terraform infrastructure for both the Kubernetes cluster itself, as well as all the platform components that are installed on top of it. In this last slide, before we get to questions, we also added some useful links that should help you get started with Kubeflow in general, and will be accessible in the posted slide deck on the Stratosphere website. This concludes our presentation, and we should have about 5 minutes to take any questions from the audience.